In this session, we are going to solve a problem named Travelling Salesperson Problem using branch and bound technique. The main objective of this problem is to find a route such that a salesperson will visit all the cities exactly once and return back to the starting city with a minimal cost. Since this is related to minimization problem, we need to find a lower bound, LB. So that lower bound is found by using a formula CEL of S by 2. What is this S? S is the sum of two closest cities of a city for all the cities. So you will understand it when we solve a problem. Here is the graph in which there are 5 cities named A, B, C, D, E. The assumption is the salesperson should start from the city A, and assumption number 2 is city B should be visited before C. So before solving this problem, we will try to find out the lower bound. As I already said, lower bound LB is CEL of S by 2. S is the sum of closest distance of a city for all the cities. That is what I mentioned. So here, how to find LB? LB is sum of the closest distance of two cities of a city. For city A, the closest distance is 1 and 3. So it is 1 plus 3. This is for A. For B, the closest or the shortest is 3 and 6. So it is 3 plus 6. For city C, the closest distance is 1 and 2. For D, the closest distance is 3 as well as 4. So 3 plus 4. For E, the closest distance is 2 and 3. So 2 plus 3. Divided by 2, and it is the CEL. So when you add all these, you will get 28 by 2, which is 14. So this is the lower bound. So we need to construct a state space tree for solving this TSP. So while solving that TSP, the state space tree will be, since I am starting with vertex A, let me name it as A, and the lower bound is 14. So this is my root node. Then from A, where can I go? To C, to B, to D, as well as to E. So the various nodes that can be explored are AB, AC, AD, as well as AE. I need to find the lower bound for all these edges. So, how to find the lower bound of edge AB? The edge which I am considering here is AB. So, how to find the lower bound for the edge AB? In this case, the lower bound will be summation of, here also I need to consider all the cities, but the edge AB should be included definitely. So for A, this AB should be definitely included. So it is 3. And for B also, this AB should definitely be included. So I am placing 3. Other than this, which is the closest to A? It is 1. Other than AB, which is the closest to B? It is 6. This AB is no way connected with C, D and E. Therefore, we will have the same value as 1 plus 2, 3 plus 4 and 2 plus 3 for the other cities. So when you add all these, you will get 28 by 2. Seal of 28 by 2, which is nothing but 14. So here I will place 14. Now I need to find for this AC. This AC should not be visited. Why? Because we have an assumption B should be visited. B should be visited before C. So if we take the edge AC, B is not visited before C. So we should not explore this. Coming to AD. Now we need to find for edge AD. So the lower bound for AD will be definitely the edge AD should be included. For sure, the edge AD should be included for two cities A and D. So AD, the distance is 5. B is nowhere related to this edge. So whatever is there here will be copied here. C is nowhere related to the edge. So whatever is here will come here. But D is included. So definitely the edge AD should be considered. So it is 5 plus. And E is nowhere related to this edge. So the same thing, 2 plus 3 by 2. So remaining, I need to find the closest with A and D. So closest with A is 1 and closest with D is 3. So when I add all these, I will get 31 by 2. So it is actually something 15 points it will come. 15 point in points. So if I find the seal, it will be 16. Next, I need to find, so now I am updating the state space tree, it is 16. Next for the edge AE. So for the edge AE, definitely this edge should be included for two cities A and E. So the values will be 8 plus something for A, and for B it is nowhere related, so same 3 plus 6. C it is nowhere related, so same 1 plus 2. D is nowhere related, so same 3 plus 4. E is there, therefore definitely AE should be included, which is 8 plus something. So which is closest to E? That is 2. And which is closest to A? That is 1. So when I add all these, I will get 38 by 2, which is 19. So that I am updating here. Of all these, this is the lowest. Since this is minimization problem, I have to concentrate on the minimal value. So of all these, this is the minimal. So I am exploring this one. So I have visited B from A. So various options left are from B, where can I go? To C, to D and to E. So I have three options. I can go to A, B, C, or else I can go to A, B, D, or else I can go to A, B, E. So I need to find the lower bound for all these cases. So how to find the lower bound for all these cases? Let us start with ABC. ABC. So here, what all edge should be included? I definitely have to consider the edge AB and the edge BC. So my lower bound will be seal off. So definitely the edge AB should be there. So for A, this AB will definitely come. So AB is 3. And for B also it will come. Then C, BC, this edge should be considered. So BC is 6. So that is applicable to both city B as well as C. So definitely it should be included, 6 and 6. Whereas D is nowhere related, so same 3 plus 4. And E is nowhere related, so same 2 plus 3 by 2. So what else is remaining? for A, one more I have to add. The closest one is 1. And related to C, the closest one is again 1. So when I add all these, my answer will be 32 by 2 and it is 16. So I am updating here. Next, I need to find A, B, D. In this, I have to include edges AB and BD. Two edges need to be considered. So how to find the lower bound for this? Seal off. So as far as A is concerned, definitely the edge AB should be included. As far as B is concerned, definitely the edge AB and BD should be considered. So AB, it is 3. So 3 will come for A as well as for B. Whereas C is nowhere related to this edge, so same 1 plus 2. D is there, edge BD is there. Edge BD is there, therefore here BD 7 should be included in both B as well as in D. And E is nowhere related to this ABD, therefore the same thing 2 plus 3. So what else is remaining? For A, I should include one more closest path, which is 1. And for D, I have to include one more closest path, which is 3. So if I add all these, I will get the lower bound as 32 by 2, which is 16. So let me update here. This is also 16. Now let me find for the edge A, B, E. In this, the edges AB and BE should be considered compulsorily. So how to find the LB? So the same formula, seal off, I have to include the edge AB definitely. So AB is 3. That is applicable for city A as well as for city B. And then as far as C is concerned, it is nowhere related. So I will simply copy whatever is there in C in my first calculation. So D is not there in D, city D is not there in any of the edges. So I will copy the same 3 plus 4. Whereas E is there. So the edge BE should be definitely considered. What is edge BE? It is 9. So 9 should be considered for E as well as for B. So what is the remaining? A should have one more thing and E should have one more thing. A, it is 1, the closest distance, and for E, the closest distance is 2 by 2. So if I add all these, I will get 35 by 2, which is around 17 point something. And the seal of which will be 18. Okay. So let me update the state space tree. So of these three, this is 16, this is 16 and this is 18. The minimal should be considered. So since these two are equal, I will explore both. So from A, B, C, where can I go? A, B, C is visited. Then where can I go? Either to D or to E. So that is A, B, C is done. From C, I can go to D or else E. So if I go to D, what will happen? And if I go to E, what will happen? So if I go to D, from A, B, C, if I go to D, what is the last option that I have? E. And from E, where can I go? To the starting place A. In this case, A, B, C is here. After that, I can go to E, and from E, I can go to A. In this, A, B, C, next I am going to E. From E, I can go to D, and then from D to A. So these are the options. So A, B, C, from C to D, then D to E, then E to A, or else A, B, C to E, from E to D and D to A. Similarly, in this case, I have already visited A, B, C. The only option left is A, B, C, D. Sorry, A, B, D and C. I'm sorry. So it is A, B, D, C, or else A, B, D, E. So if I have reached A, B, D, C, the left city is E, and then from E I can go to A. So it is EA here. If it is A, B, D, E, the left city is A, C, and then from C I can go back to A. So these are the options. For all these options, I need to find the lower bound again using the same formula. So let us see how to find out it. So for A, B, C, D, E, A. So what are the edges we need to consider? AB, BC, CD, DE and EA should be considered. So if it is considered, the lower bound will be seal off. So for city A, definitely AB should be considered. So it is 3. For B, I have two edges, AB and BC. So AB is 3, BC is 6. For C, two edges should be definitely considered, BC and CD. So BC is 6, CD is 4. Then for D, two edges, CD and DE should be compulsorily considered. So CD, it is 4 and DE, it is 3. For E, these are compulsory. So DE is 3 and EA is 8. And for A also, AB and EA should be considered. So AB is 3 already we have noted, and EA it is 8 by 2, seal. So if I add all these, I will get 47 by 2, which is seal of 23.5, that is 24. So I am updating in the state space tree. So LB is 24. Next, I have to find the LB of this one. So the edges are AB, CE, DA, AB, BC, CE, ED and DA. So the lower bound is so definitely with respect to city A, AB and DA should be included for sure. So AB, it is 3. DA, that is AD, it is 5. For B, definitely AB and BC. AB is 3, BC is 6. For C, definitely BC and CE. BC is 6, CE is 2. For D, definitely ED and DA. ED is 3, DA is 5. For E, definitely CE and ED. So CE is 2 and ED is 3 by 2. When I add all these, I will get 38 by 2, which is 19. Let me update here. So LB is equal to 19. Now I have to find for the next one. So it is A, B, D, C, E, A. So A, B, D, C, E, A. The edges to be considered are AB, BD, DC, CE and EA. So LB is seal off. Here is the graph. So for A, I have to consider, definitely I have to consider the edge AB and the edge EA. For B, definitely AB and BD. For C, these two. For D, these two. For E, these two. So when I update, it will be, for A, it will be, from the graph, it is 3 plus 8 plus 3 plus 7 plus 4 plus 2 plus 7 plus 4 plus 2 plus 8 by 2. And the answer will be 48 by 2, which is 24. Let me update here. So LB is 24. Now I have to find the last option, which is A, B, D, E, C, A. The edges to be included are AB, BD, DE, EC and CA. So same lower bound. I am calculating with the help of the graph. So for A, definitely the edge AB and CA should be considered. For B, AB and BD. For C, these two. For D, these two. For E, these two should be considered. So if I include that, my answer will be 3 plus 1 for A, 3 plus 7 for B, 2 plus 1 for C, 7 plus 3 for D, and 3 plus 2 for E divided by 2. And if I add all these, I will get 32 by 2, which is 16. So now let us update here. LB is equal to 16. So of all these, the minimal is this one. So this is my optimal solution. This is my optimal solution. So my tour is, I am going from A to B, then to D, then to E, then to C, then to A. And the cost is 16. So since this is a minimization problem, I have to consider the minimal amount, which is 16. Comparing this 16 with all other leaf nodes, I have to select or kill it. So since this is 24, which is greater than 16, I will consider this node as inferior. This also inferior. This also inferior. 18 is also greater than 16, so inferior. 19 is also greater than 16, so inferior. 16 and 16 are equal, but here I have visited just 2 cities. So if I explore further, definitely it will also end up in higher values. So this is also considered as inferior. So for the given graph, this is the state space tree, and the tour is given A to B, B to D, D to E, E to C and C to A, and the cost of the minimal cost taken by the salesperson is 16.